ये यूज कर रहे थे. Okay. So the problem number 3 is about the surface of revolution. The computation for this problem is the same, so one can easily do problem number 3 also. For the last one, problem number 4, the surface is z equal to fxy. Computation for this also will be the same. The only thing that you have to see over here, that the position vector in this case will be x y f x y. We have to compute the second fundamental form first also. So, the parameters over here are x and y, and therefore, r 1 is the derivative of r with respect to x, which is 1 0 and you may call it f x. Then second r 2 will be 0 1 and this you may call f y, f x partial derivative of f with respect to x. Similarly, f y is partial derivative of f with respect to y. Now, then we have to compute r 1 1, this will be the derivative of r 1 with respect to x. So, this is 0 0, second order derivative of f with respect to x is f x x. Similarly, r 1 2 is 0 0 f x y, r 2 2 is 0 0 f y y. So, these are the second order derivatives, you may call them r I j's. So, these 3 derivatives are r I j's. Then n you can easily compute from here. So, n from here can be computed as r 1 cross r 2 upon modulus of r 1 cross r 2. This is a standard, one can easily compute it. Then you have to compute b I j's, that is b 1 1, b 1 2 and b 2 2. b 1 1 will be n dot r 1 1. So, r 1 1 is there and can be computed. So, this will give you a scalar. Similarly, b 1 2 is n dot r 1 2 and this is n dot r 2 2. So, all these computation is straightforward, one can easily do. So, this much I am leaving for you. So, the next topic is the Gauss map, the Gauss map of a surface. Gauss map, Gauss map and Gaussian curvature. Same Gauss. Okay. So, the Gauss map. So, what we have in this case, we have a regular surface as usual given by this equation r equal to r of u 1 u 2. I will assume throughout that this is a regular surface of at least class 2. So, suppose geometrically it is drawn over here in R 3. Let me call this surface as sigma. Also in R 3 you draw the unit sphere. This is a unit sphere S 2. This is also drawn inside R 3. So, both this and this are lying in the same space, but we want to see what is the map. So, the Gauss map is a map between the surface sigma to the sphere S 2. How does it work? Let us see. If you choose an arbitrary point P on the surface, the Gauss map G will map it to some point P star, and this point P star is such that the normal at the point P, say unit normal n at P, it will be same as the position vector of P star. So, OP star. So, G is the map from the surface sigma to the unit sphere S 2, and it is such that it maps a point P to a point P star such that OP star, the vector OP star is precisely the unit normal to the surface at the point P. This is how the Gauss map works. So, this is the definition of the Gauss map. I am not writing any language, I am just indicating how it is defined. The language is there in the notes as well as in the book. So, no, I need not write down the whole definition. All right. All the symbol are standard and always stands for unit normal, etc. All right. Then I will talk about the Gaussian curvature of the surface sigma. So, what we do, the Gaussian curvature. So, suppose I choose some region around the point P on the surface. So, under the Gauss map, if I call this region as omega, under the Gauss map G, this region will be mapped to a region over the sphere, you may call it omega star. So, let a region omega on the surface sigma is mapped to a region omega star. Okay. Now, I choose this region, this contains the point P, okay, because Gaussian curvature will be discussed at a point P of a surface. So, this region will definitely contain the point P star. Okay. Now, the Gaussian curvature at the point P, what it is, let us understand. Okay. So, the Gaussian curvature K at P is defined as K at P is equal to area of omega star upon the area of the region omega, in the limiting case when this omega shrinks to the point P. This shrinking is denoted by this symbol. Okay. So, when you shrink this region to the point P, this region too will be shrinked. So, what will be the ratio in the limiting case? That is exactly what the Gaussian curvature is. Okay. So, this is the definition of the Gaussian curvature of a surface at a point P. Yes, it tells you the curvedness. What actually you are doing here is you are comparing your surface with a sphere. Okay. You are sitting with a surface and a sphere, and you are seeing that how the deviation of the surface vis-a-vis a sphere is changing, because a sphere is a very ideal kind of a surface. It has a same curveness everywhere, but our surface will change its curvature at every point. Okay. So, how does it behave vis-a-vis the sphere? That is what we see. So, we are looking at the curvature measure of the surface with an ideal surface, a sphere. Okay. Now, when we will work out its expression, that the idea will be more clear. So, expression for Gaussian curvature. All right. So, what we will be doing, we will consider the determinant Bij. So, consider B. If you look at B, then this was in fact the determinant of B I j, and that is in fact B 11, B 22 minus B 12 into B 21. And let me simplify it. B 11 is minus times n 1 dot r 1. So, minus times n 1 dot r 1. Similarly, B 22 will be minus time n 2 dot r 2. So, this minus minus plus. Here also minus in the 2 term will make it plus. So, this is n 1 dot r 2 into n 2 dot r 1. Okay. Now, this I will write down like this: n 1 dot r 1 into n 2 minus n 2 dot r 1 into n 1 dot r 2. If I call this as A vector, this vector as C, this vector as B. Okay. So, this vector this vector A dot C into B. So, it should be, this should be A and this should be C. Okay. So, this is A dot C into B minus A dot B into C. Am I right? A dot C into B minus A dot B into C. A dot C into B minus A dot B into C. So, this is the cross product of R 1 cross N 1 cross N 2. Okay. And this whole thing dot R 2. Okay. Now, I can write down this as minus times n 1 cross n 2 dot cross R 1. Okay. Okay. Is it okay? Positive. If I interchange, there will be negative sign, but it should not be negative. It should not be negative. In fact, this should have been written, this A cross B cross C, this formula is for A cross B cross C, or it is like this. क्यों भाई कौन सा है? So, we are writing this becomes n 2 dot r 2 n 1, r 2 dot n 1 n 2 and r 2 r 1 outside. R 1 is here, R 1 is here, I take it out. So, now you compare it with the formula of A cross B cross C. So, this is A, this is B, this is C. So, it becomes A means R 2 cross B cross C. So, n 1 cross and 2, and then dot with R 1. So, now I can interchange dot and cross in this triple product. So, this is R 2, this is N 1 cross N 2, dot R 1 cross R 2, and the left side is B. So, B is this, you may call it number 1, and now use the formula of dot product over here. So, it is modulus of N 1 cross N 2 into modulus of R 1 cross R 2 into cosine of the angle phi between R 1 cross R 2 and N 1 cross N 2, where phi is the angle between N 1 cross N 2 and R 1 cross R 2. Now, observe that R 1 cross R 2 is parallel to N, and N 1 cross N 2 is also parallel to N. Why? Because N 1 dot N is 0, because N dot N is 1. So, N 1 dot N will be 0, and 2 dot N will also be 0, and therefore, N is perpendicular to N 1 and N 2 both, and this implies N 1 cross N 2 is parallel to N. So, N 1 N 2 as well as R 1 cross R 2 are both parallel to N. So, this implies that R 1 cross R 2 is parallel to N 1 cross N 2, and this means the angle phi is 0, and this means cos phi is 1, which implies cos phi is 1, and therefore, from here I can write down B equal to simply N 1 cross N 2 into mod of R 1 cross R 2, and this will give me that N 1 cross N 2 mod is equal to B upon modulus of R 1 cross R 2, and modulus of R 1 cross R 2 is under root g. So, this becomes B upon under root g. So, N 1 cross N 2 is B upon under root g. This is an important relation which I will call as number 1. Okay. Now, come to the definition, Gaussian curvature. So, by definition, by the box definition of Gauss curvature, now by definition Gaussian curvature K, which is written here, is the limit of area of omega star upon area of omega, when omega shrinks to the point P. Area of omega star. So, position vector of any point in omega star will be what? Will be along n. This is the definition of the Gauss map, OP star equal to n. So, the position vector of a point inside omega star is n. Okay. So, this will be, and when you have the position vector of a region on a surface, suppose this is the position vector, you consider R, then what is the area? Area of this region is R 1 cross R 2 du 1 du 2 double integral. So, this I should replace by n for the sphere. So, the area will be replaced by n 1 cross n 2. So, on the sphere this area will be double integral of n 1 cross n 2 into whatever the parameter is d theta d phi whatever, okay. And over here it will be modulus of r 1 cross r 2 into d u 1 d u 2, the limit omega tends to p. Okay. So, now the limiting case, the ratio of the integral will be same as the ratio of the integrand in the limiting case. So, this will be same as n 1 cross n 2 mod integral will go off upon modulus of r 1 cross r 2. n 1 cross n 2 we had just computed, it was b upon under root g, and mod of r 1 cross r 2 we already know it is also under root g. So, it becomes simply b upon g. So, the Gaussian curvature k is given by the formula b upon g, k is equal to b upon g. I stop at this point, we will be solving exercise on it in our next lecture.